This video is going to go over the basics of ionic bonding, Lewis dot structures, naming ionic compounds, and how to make formulas for ionic compounds. Chemical bonds are forces that hold atoms or groups of atoms together. In an ionic bond specifically, there's a transfer of valence electrons that happens. You probably remember from when we talked about classifying matter that compounds are a chemical combination of two or more different elements bonded together in a fixed ratio. Generally, atoms are going to combine to form a compound that's more stable than the separate atoms were alone. For example, if you talk about sodium, abbreviation is Na, that's a silver metal. And if you look at chlorine, that's a greenish-yellow gas that's actually very toxic. But then when you put those two together and make the compound sodium chloride, that is the same thing as table salt. It's a white crystalline solid, safe to eat, super stable. So that's an example of two elements combining to make a compound that's totally different than the elements that it made up before. If you remember back to our periodic table unit that we just finished, we talked about how most elements want an outer valence shell that's full of 8 electrons. That's the most desirable and stable state for most atoms. We call this the octet rule. The octet rule can be simplified in the kind of catchy phrase, 8 is great. So if you think about having a full shell of 8, that's great. It's the most stable for most atoms. So in ionic bonds, electrons are going to be either gained or lost. And they're gained or lost in a way that makes the compound more stable. Just to review, valence electrons are the same as the group number of each group or family. So if we take a look at the periodic table, if we look at group 1A, it's going to have 1 valence electron. Those two things go together. Group 2A is going to have 2 valence electrons. You skip over the transition metals because their valence electrons vary. Pick up again after the transition metals at group 3A, the boron group. It has 3 valence electrons. Group 4A, the carbon group, has 4 valence electrons. Group 5A, the nitrogen group, has 5 valence electrons. Group 6A, the oxygen group, has 6 valence electrons. Group 7A, the halogens, has 7 valence electrons. And group 8A, our noble gases, has a full shell of 8 valence electrons. So here's a quick question. Group 8A, or group 18, the noble gases, rarely form compounds. Why do you think that is? Well, the answer's here, but basically the reason why is because they have a full set of 8 valence electrons already. All of them except for helium here, you can see they have 8 valence electrons because they're in that group 8. So they're going to be what we call inert, or not reactive. The oxidation number, or the charge of ions, is what they use for bonding. It shows up as a superscript, or like a number that's kind of raised up like this, and it's behind the element, and it includes the electromagnetic charge and the oxidation number. So it's going to have either plus or minus, and the oxidation number. And remember, everybody wants to have 8 valence electrons. So what's going to happen is things are either going to lose or gain electrons to get to either 8 or to get to 0, which would bump them down to their next lower shell, which would have 8 in it. So, for example, if we look at barium, it's in group 2, and group 2 has an oxidation number of +2, so you would just put that little +2 as the superscript. If you see something like this chlorine one where there's just a negative, you assume that that means -1. If there's no superscript, that means there's no charge at all. So if you just had Cl and nothing there, that means there's no charge. But if you see just a plus like this or just a minus like this one, that means either -1 or +1. They just don't usually write the 1, it's more implied. So here's a quick review of the oxidation numbers by each group on the periodic table. So your group 1 here, starting with hydrogen, has an oxidation number of +1. Group 2, starting with beryllium, has an oxidation number of +2. Remember, we're always going to skip over the transition metals because those have varied valence electrons and varied oxidation numbers, although usually the oxidation numbers are either going to be +2 or +3 on transition metals. If we go over here to our group 3 that starts with boron, it has a +3 oxidation number. Group 4, the carbon group, this is where it starts getting tricky. That group can be either plus or -4. The nitrogen group is where it starts going backwards, so they have an oxidation number of -2. -3. The oxygen group, the next one over, that one has a charge of -2. The halogens, group 7, have a charge of -1. And then our noble gases, they have an oxidation number of 0. Remember, these noble gases over here are the ones that are not going to react with anybody because they already have their full set of 8 valence electrons. One thing about oxidation numbers that is kind of tricky for people sometimes is it seems a little backwards when you look at the charge and what that means about what's happening to the electrons. So if you have a positive oxidation number, that means that you are losing electrons. If you have a negative oxidation number, that means that you're gaining electrons. And I know at first that sounds kind of backwards, but the reason why is because remember we said electrons have a -1 charge. So if you lose 1 electron, that's like subtracting -1. And if you remember from math, subtracting -1 is the same thing as adding 1. So if you lost an electron, that means you're going to end up with a positive oxidation number. If you gain an electron, that's like adding -1. So you're still going to get a negative for that. So if you see a negative oxidation number, that means it gained an electron. Going back to ionic compounds have an attraction between the positive ions, which are called cations, and the negative ions, which are called anions. And electrons are going to transfer from the positive metals to the negative nonmetals. So you can see here in a sodium ion, it's going to lose an electron to become sodium +1. Chlorine ions, the nonmetal, is going to gain an electron to become chlorine -1. And then when they bond together, like you can see in this last step, the chlorine -1 is going to go together with the sodium +1, and they're going to form a compound. So this shows them bonded together in an ionic compound. Here's another way to show the same thing that we looked at on the last slide. So we've got our sodium atom here, and here's its 1 electron that it's going to lose. You've got your chlorine atom here, and that electron it's showing is going to move over and be gained by chlorine. So then what you'll end up with in your ionic compound is you have a sodium ion that lost 1 electron, so it has a +1 charge, and a chloride ion that gained 1 electron, so now it has a -1 charge. So here's a quick question for you. Which one of these elements is most likely to donate 1 electron? And if it's donating 1 electron, that means it would have an oxidation number of +1, because remember, plus means you let 1 go, you lost 1. So the group on the periodic table that has a +1 oxidation number is group 1, your alkali earth metals. And the only thing on here that's in that group is cesium. The rest of those are not in group 1. Okay, now we're going to look at how to draw electron dot structures. Electron dot structures look complicated, but they're really not. They're just the symbols of atoms, and they have little dots to represent the valence electrons. So we remember from earlier that the valence electrons go with the number of the group. So if we look at our group 1 over here, these all have one valence electron. So when you draw them with one dot to represent that one valence electron. See the same thing with group 2, two valence electrons, so those all have two dots. And you can see that it goes from 1 through 8, you add dots each time. The only kind of weirdo here is helium. Helium's sort of unique because it doesn't need 8 electrons to make it happy. It only needs these 2. So that's just kind of one that you're going to have to remember because it's the odd one out. It doesn't follow the same pattern. Here's a quick little learning check. So this here, that Lewis dot structure, could be an electron dot formula for what? Well, I can see it's got one valence electron, so it could be anything in the the alkali metals, group 1. So it could be hydrogen, could be lithium, could be sodium, could be potassium, could be rubidium, could be cesium, or could be francium. Any of those group 1 elements. Let's look at the second one. So this one, we've got 5 valence electrons. So we know it's going to be something in group 5, the nitrogen group. And the only, boron is in group 3, so it can't be that one. Nitrogen's in the nitrogen group, so it could be that one. And if you look really closely, phosphorus is actually in that group too. So it could be 2 or 3, could be the answer. Okay, let's go over a couple properties of ionic compounds. So ionic compounds are generally solids at room temperature. They're non-conductive as solids. They dissolve in water by a process called dissociation. They are conductive when they're dissolved. They usually have high melting points, and they're hard, brittle crystals. Here's a little image depicting ionic solids being dissociated or dissolved in water. Now let's talk about how to write formulas for ionic compounds. So when you're writing the formulas, what you're going to do is you're going to write the symbol for the positive ion or the metal first, followed by the symbol for the negative ion or the nonmetal second. And remember also the positive ions are called cations and the negative ions are called anions. So you may see any of those words, you have to know what they mean. Okay, then you're going to assign subscripts to make sure the compound is electrically neutral, which means you're going to have to cancel out the charges. So here's an example up here. We have calcium. So calcium is the positive ion. It has a +2 charge, so you just write it with that superscript +2. It's going to combine with chlorine. So chlorine has a -1 charge. Remember, you don't have to write the 1, just the negative. So when we write the formula, you're going to put the positive one first, -1 second, and then what you have to do is make sure that the charges equal 0 if you add them together. That's what makes a neutral compound. So here you can see that if calcium has a charge of +2 and chlorine has a charge of -1, you're going to have 2 chlorines for every calcium for it to be neutral and add up to 0. A trick that you can do that can kind of help you out with this, if it's hard for you to do that math in your head, is you can write out the compound with the charges, and then you can take these numbers on the charges and crisscross them. So the 1 will come down here, and the 2 will come down here. Remember, we don't have to write 1, so I'm just going to leave this one as calcium. And then with chlorine, put the little 2. And you see, I got the same answer doing the crisscross method as they did doing it kind of the mental way in your head. So whichever way is easier for you, you can do. All right, let's do a couple examples of these together. So if you're doing a formula for the ionic compound of sodium and oxygen, we've got sodium +1 and oxygen 2-. So if we do the crisscross method, that gives us Na2O. That'd be number 2. Okay, aluminum and chlorine. Aluminum in this case has a +3 charge. It's one of those, it's in group 3, so that's how you know it has a +3 charge. Chlorine has a -1 charge or oxidation number because it's in group 7. And then we just got to crisscross the charges to make it neutral. So you would get answer 3 here. And the last one, formula for iron +3 and oxygen -2. So if we crisscross those charges, we would get Fe2O3, which is answer number 3. Okay, the last thing we have to do with ionic compounds is we have to know how to name them. So basically it's 2 steps. You're going to name each element. Remember, do the positive cation first, the negative anion second, and then end the last element in IDE, or IDE. So for example, if you have MgCl2, first one is magnesium, so you write magnesium, and then the second one is chlorine. There you go, there's step 1. You just named each element. Step 2 is to change the ending of the second one to IDE. So you just change it from INE to IDE. So the name of this compound would be magnesium chloride. Pretty easy, right? When you have ionic compounds that contain the transition group elements, it can be a little more complicated. So with these, you're still going to name the metal first, the positive ion, and then the nonmetal second, the negative ion. But many of the transition elements, like we said, have variable charges. So historically, they have these fancy names. And if there's 2 different charges, you use the suffix "ik" for the higher of the 2 and the suffix "us" for the lower of the 2. So like for iron, like these 2, iron +2, the higher or the lower one would be called ferrous. And iron +3, the higher is called ferric. So that's kind of the old way. We don't really use that as much anymore. You might see it, but usually what you'll do is what you see here. You just name the ion, but after the name of it, you follow it by a Roman numeral that indicates the charge. So for iron +2, you just put iron and then the little Roman numeral 2 in the parentheses. And for +3, you just put the 3 in parentheses. One other thing that can make naming ionic compounds a little bit more complicated is we have these things called polyatomic ions. And they're basically a charged group of covalently bonded atoms that works similar to an ion. So it's going to bond ionically to an oppositely charged ion, just like what we've seen before. The good news for y'all is that they're all listed on the star chart, so you don't have to memorize them. So if you take a look at your star chart, you should see examples like these ones down here. And they're just several elements together that all stay together as an ion, and they'll always have a charge. So basically when you're naming, if you see something like this, NO3 -1, you're just going to name that nitrate. You're not going to say nitrogen, 3 oxygens, and a -1. You just call it nitrate. So look on your star chart and try to become familiar with those when you're naming ionic compounds.